the winners of the startup challenge will be announced. There is a pit stop for all VentuRISE semi-finalists. And for all of those who have already applied and who are on this particular call, your applications are being reviewed as we speak. And we will, be announcing the semi-finalist soon. For those of you who have joined and or yet not completed their applications forms, our sincere request to you is to do that really, really quickly because time is running out. And as you probably know, this startup challenge actually has, in addition to a 300,000 USD prize money pool that startups can actually avail of, there are a bunch of other benefits that are there, which include participation in the Thai Global Summit in December 2024, where there is a full day track that we are putting together, a session on ESDM, a session on aerospace and defense, and also a session on the EV and clean mobility. So it's a full day track that we are doing. Opportunity for startups who would have completed their applications and are part of the semi-final list to actually connect with potential mentors, investors, also corporates will be participating in the track. Now, these are some of the mentors whom we have been onboarded. You can see them on the screen. One of those mentors, of course, is Gadhadar. He's actually on this call, but more about Gadhadar in a bit because we will, actually, it's a great opportunity for people to know the set of stellar accomplishments that Gadhadar has. We will talk about that in a bit. Yeah. Now, very quickly, the deadline that we have currently is the 15th of November. We would encourage all those who are on the call who are yet to complete their forms to please complete it so that we can actually take your application, go and run it through the entire first evaluation process. Just for before I kind of wind up on this, for all those semi-finalists, as I mentioned, will actually participate at the Thai Global Summit in December. They will, people who are interested can actually also take a booth or something if they want. Once the Thai Global Summit concludes, we will then get started with the jury evaluation process and also the mentor connects for those startups who move up to that stage. This is all in preparation for the finale that will happen in February. Okay. So I will stop at this point and I will hand it back to Vinay to get the next set of the program going.
Yeah. So now we're going to have TRA, sir, TR Anand, who's a Thai board member, and he leads the deep tech community at Thai, the Matrix Forum, to introduce Gadhadar. Over to you, sir.
Yeah, thank you. Thank you, Vinay, and thank you, Rajesh. And a warm welcome to all the startups who are participating in this webinar mentoring, pre-mentoring session, as I call it. So it sounds exciting, and I think you're here because you all have accepted the challenge. It's a great opportunity to showcase your startups and actually participate in setting up your company with focus on manufacturing in Karnataka in these three areas that Rajesh outlined. And the government is very keen to be able to promote, and Karnataka has always been at the forefront of leading all these technology areas. And that's the reason why we are here today. And Thai Bangalore, as a partner of GOK for a decade or more, has been a part of all their initiatives, starting from Elevate 100 right down to these programs. And we focus on VentuRISE edition 2.0 this year. So warm welcome. And the way we have planned it is that we thought that it will be good for you to actually talk to and listen to and have your questions answered by a very accomplished startup who's always also been a Government of Karnataka Elevate 100 participant winner, and amongst many other accolades that they have got. So it's a real pleasure to identify one of the mentors who's going to be taking you through these till February when the GIM Global Investor Meet happens. So without further ado, it's my pleasure to introduce Mr. Gadhadar Reddy. He's a distinguished entrepreneur with expertise in the field of nanotechnology. Nanotechnology is a field which has been in the forefront of leading a lot of innovation in terms of the tech space being deployed across a variety of industries in space, defense, water, electronics, in almost every part of our daily life. And he's a very early entry into this particular area. He's the CEO of NoPo Nanotechnologies, and he has successfully developed and not just developed, but achieved a breakthrough manufacturing technology in carbon nanotube CNTs. And this forms the forefront of the deployment of nanotechnology in many of these areas. So numerous sectors are identified, and making carbon nanotubes as available to all these industries as a core component. Many accolades, and I'm not going to go through all his education, etc. Obviously, they're all very accomplished, and he's also worked with a number of people, including Nobel laureate Dr. Richard Smalley. NoPo Technologies is among the top 5 carbon nanotube manufacturers in the world, a top 3 winner in Global Startup Challenge. You couldn't have had a better person than him to lead this conversation and mentoring space in this extent. His work has been featured not just in manufacturing, but also in peer-reviewed journals, including Nature. Okay, so it's a pleasure to introduce Gadhadar Reddy, and over to you for the rest of the session today. Thank you.
Over to you, Gadhadar. I think you're on mute.
Yeah. Awesome. Thank you very much. I appreciate that. So hello, everyone, and thank you, Rajesh and Vinay, for putting this together. So as TRS just mentioned, we are a startup that's been working on carbon nanotubes for quite some time now. And this particular talk, the idea was to share with you on the methodologies that we have used and developed over time to be able to develop these technologies. And what is it that we have seen? And over the years, I've had the fortune of having spent time at 2 different innovation ecosystems. One in the Silicon Valley as part of a program called Singularity University, where I spent time at the NASA Ames Research Center learning about how Silicon Valley works. So the basic idea was to spend 6 months there trying to understand how the valley works, how innovation happens, how technology is created. Then I was able to apply that to what we're creating at NoPo in Bangalore, and later spent time at Oxford, again, as part of a program called CRISP, understanding the same thing. So I'm happy to share these learnings with everyone, and anyone questions, please feel free to use the chat box and type in your questions, and post the talk to can spend a significant amount of time talking about these and answering your questions or answering more specific questions, so it's more helpful for you at the end of it. So the way I've structured this today is to tell you about how we have built this material. Preceding that would be why we are building it in the first place, because the why is what leads to going to the next steps, and also about how we found customers outside of India and within the country, and how we are scaling operations with those customers. So we'll get started in that direction. So first thing is, when it comes to advanced materials, there are a lot of them. So advanced materials are mostly materials that we create using the human intellect, more than having nature create them. So there's a point at which nature has given us a lot of stuff, and we are not happy with what they can do. So we want something more. And this has led to creation of newer materials. And in this talk, I'm going to pepper it with a few books that you can always go back and refer to that talks about technology development. This book in particular is actually an excellent introduction for anyone working on materials. It talks about silicon, it talks about nanotubes to an extent on how the development happened, steel, and other varied sectors. So one very interesting aspect on any kind of technology development is for one person to be able to champion the technology. That is, you need to have somebody who is extremely passionate about any technology and who is willing to back that technology. So often it so happens that we'll have a choice, like we'll have three, four options, and we'll have to choose one. And someone has to be that one who's going to push for that technology. So that is what would be the lessons we learn from these. Now, let's start with the nanotubes themselves. I'll give you a brief understanding of what this material is all about. Now, nanotubes, they come in multiple varieties. We have something called single wall nanotubes. We have something called multi-wall nanotubes. And nanotubes are very, very tiny. So each tube is about 1 to 2 lakh times smaller than a hair strand. Imagine a single hair strand, and imagine something about 1 to 2 lakh times smaller than that single hair strand. So now when we make something so tiny, it starts behaving in a very different way from objects that are there in the real world. So these start having very high conductivities. They're extremely strong. They're up to 100 times stronger than steel is, and they're extremely light. Now, the diameter of these tubes, when we talk of these 0.5 or 1.5 nanometers and stuff, so the dimension we are talking about is actually very, very tiny. This is, in fact, the size is measured in atoms. That's you're talking of 10 to 15 hydrogen atoms as a diameter. The tubes that we produce at NoPo, their dimensions are only about 10 atoms. And I'll be talking about how we develop such advanced technology where you're able to produce something with an atomically precise accuracy and being able to do that here in Bangalore. Okay. So a little history about nanotubes. So on how these were formed. So what is interesting is with all these materials and with inventions and discoveries, we have a lot of interesting loops that happen. So the work really started in the 80s. So in the around the 80s, there was a professor called Kroto who had been observing starlight. And in the starlight, he was able to see spectra that resembled carbon, but did not resemble any known form of carbon. So he had been seeing that, and he couldn't make sense of it because even if you go back to our schooling and we look at our textbooks and what we read, we always saw that we knew all the forms of carbon, right? We had a carbon black, graphite, and it's like you had the seven allotropes of carbon, and that's it. There's nothing else to know about it. And suddenly he's looking at starlight, he's seeing a star material that does not make any sense. And while looking for meaning for this, he came across a professor called Smalley. Smalley happened to have the world's most powerful laser. And like with any boy with a powerful gun, he was just firing everything. And he decided to fire this against a carbon structure with iron because Kroto said he had been observing iron particles also with it. So when they fired this super powerful laser at the carbon containing structure with small iron particles, they were able to see the same spectra, the starlight spectra that they were seeing in this material. So then they realized, okay, so this must be something that is giving this. And when they put it under a microscope, they found this football-like structure. And this football-like structure is known as a fullerene. You can see on the top image. That's a very big zoomed out image of the fullerene. It's built out using existing macro structures. In reality, each fullerene is another 2 lakh times smaller from football-like structure that's being held up by Kroto in the picture above. So to make it so tiny, it was like crazy. That okay, so there is a new football-like molecule that's being formed, and that is able to do this. So this is known as a Buckminster fullerene, C60. So this is where the journey started. This was in 85, and soon after the discovery, Smalley, Kroto, and Curl, they won a Nobel Prize. Normally, Nobel Prizes at that point were being awarded to people who had discovered something back in the 30s and 40s, and suddenly were getting a Nobel Prize for some discovery just a year ago. So everyone started flocking into this. And very soon, Ijima, who's on the top left image in Japan, he observed that there were tubes of carbon that looked like, unlike anything that had been seen before. And he named these as a nanotube. So Ijima is considered the person to first observe carbon nanotubes in their form and showcase it. So AGMA's work suddenly created a massive amount of interest for everybody because you had another new form of carbon. Within a span of 5, 6 years, you have two new forms of carbon being built. And this form of carbon had incredible properties. It had strength, it had lightweight, it had everything that you could ask for in a material that could build the future. And so this is what caught attention of researchers across the globe. And multiple attempts were made towards building it. Now, what's interesting is when we look at methods of growing. So I spoke about how the laser beam was used at Rice University to create the first fullerenes and later nanotubes too. Before IJMA had observed nanotubes. And in fact, a lot of such work was happening at ISC under Dr. C.N.R. Rao in his lab at Solid State Chemistry Unit in ISC, where similar experiments were being carried out and similar tubes had been observed. But the first publication happened from the Japanese, and so they got the complete credit for this, even though experiments of similar stature were happening right here in India. Traditional a very, very tiny scale. So imagine drilling nano holes into a sheet of material, making tiny drops and putting catalyst particles inside them. And these particles, we are flowing gases. And these gases are then growing into crops. And this is what the nanotubes look like. So in equivalence of that, instead of soil, we have a copper sheet. Generally, it's a copper metal sheet or a ceramic sheet. We can choose either of them. And then like we grow the crops, we have the nanotubes being grown on the surface of it. These are like structures just for your reference, the matchstick here. So you have tiny structures that are growing on top of it because of this process, and then we extract them. Now, this is how the furnaces look like. This is how the system is. Now, this is what we start as a standard textbook process. This is how it works. Now, what we decided when I started off with NoPo, I was doing the same thing. I was looking at the literature. I was trying to understand what was happening with everybody, and I was trying to see what the technique that could work even better. What was something that was better? So by looking at even more simpler processes, we think of one process that seemed like an ideal case, in which scenario you don't have to grow anything on the soil. It's all about creating a black box. You pour gases into the black box, and out comes nanotubes. So this seemed like the perfect process that you just have everything in gas phase. You just keep pumping in a carbon-containing gas, and out comes the nanotubes. So this seemed like something that is easy to carry out, that was straightforward. And we decided, okay, now let's pursue that. How do we create something like that? Now, of all the techniques that exist, this is an actual image of one of the first reactors. It was built and was tested out. Over time, we have improved that significantly. So it was about trying to understand, okay, so how do we do this? How do we create a black box into which you put gases and out comes nanotubes? And what do you have to do for that? And how do you build such a machine? Now, in terms of these block diagrams on the PowerPoint, it's super simple. Like there's nothing. There's just a black box. There's a carbon-containing gas and out comes nanotubes. But to accomplish that, you have a lot of challenges that need to be solved. So the first thing is the way nanotubes are formed. So with any kind of deep technology, we're looking at a solid foundational scientific basis. You're looking at research and you're looking at data that suggests that what you're talking about makes sense. At least at the very base level, you break it down into the first principles and it makes sense. So the way nanotubes work is like this. To produce a nanotube, you need to first have a cluster of atoms, and these can be from any of the D block elements, which is the family that contains iron, nickel, cobalt, molybdenum, and all these system materials. Now, these metals, they have to form a very small structure, which is a few 10 to 100 atoms thick. Now, this is the catalyst onto which the carbon-containing gas can join. In NoPo scenario, we make use of a gas called carbon monoxide, and we make use of a catalyst iron and iron pentacarbonyl, and we break down this chemical rapidly to dissociate it into single atoms. And these atoms are then reassembled. So what happens is we're creating a condition where we have carbon atoms that are available very sparingly. We operate at very high temperatures, up to 1,000 degrees Celsius. Under these conditions, at 1,000 degrees Celsius, it's 3 times the temperature required to vaporize a human body. It's very, very hot. And the pressure that's present inside the system is also massive. the highest levels of pressure that it can reach is 100 atmospheres. 100 atmospheres is equivalent to a kilometer of water. Imagine a cube with each side of 1 kilometer filled with water. That is 100 bar pressure. So let that sink in. Like 100 bar pressure, 1,000 degrees temperature, and treating a carbon containing gas and breaking it down continuously and reassembling those atoms. So these conditions are required. So with this, we knew as a theoretical basis that it's essential to achieve these conditions. And this is the work that one of my co-founders, Dr. Kelly Bradley, did as part of his PhD. So he was a student of Dr. Richard Smalley, and this was his PhD topic, where he figured out how the first nanotubes could be made and what was a theoretical basis for producing them that could be replicated. But as an engineering project, it was significantly more challenging because there were a lot of people who tried to replicate and tried to create a system that could actually handle these conditions and failed before NoPo did. And this is the journey that I'll be talking about further in terms of the technology development itself, on how we went about creating such a difficult system that could handle all these conditions and be able to operate for significant amount of time. Now, the secret sauce of the technology or the technique that we utilized to develop these technologies is actually something that everyone would have heard about. So once again, like with my penchant for sharing references for you, this is an excellent book that talks about the methodologies to use. And we use the standard scientific method. This is the same scientific method that's taught all the way from like now the seventh grades and eighth grades, all the way to college. Like you're going to read about just these 4 steps and nothing else. So we just diligently followed these 4 steps. You can add another 2 steps into the scientific method, but basically it starts with a hypothesis, a literature survey to determine what we are hypothesizing, and if we have anything valid in the literature to be able to go further from, to carry out and plan experiments, analyze results that are coming out of the experiment, and to set the next set of hypotheses so you can repeat it. So the key thing is that you're following the standard scientific method. You don't have to do anything that is out of ordinary. If you're questioning in the right direction, and this right direction automatically comes through if you're following the scientific technique. And this is what has given you every single accomplishment that you see around you in terms of technology. It's just a very simple, straightforward 4 step process. And we'll go through this process on developments. So I'll have 2 examples that I will showcase. First is about the hypothesis of even choosing to make nanotubes. Why make nanotubes? And then how we went through the scientific to determine that and create it. And next would be for one of the components on how we go about it. Now, let's start with the hypothesis. The first step for us was why create nanotubes? What is it that we are trying to solve? What is it that NoPo was created for? So my journey, it started in Bangalore. Like I'm from Bangalore. I used to spend my childhood summer holidays with my grandparents who lived then it was the outskirts of Bangalore. Now it's like more Bangalore itself. And we used to observe like stars, and it used to be like the most fascinating and beautiful thing I could look up to. Now, as with time, as things went on, so I realized that there was a deep interest for space and wanted to have a way to go to space regularly. So one of the challenges I realized very quickly was that it's not easy to do that. Rocket science is difficult for a reason. We're pushing everything to its limits, and we are extracting every few grams and every inch of performance that we can get. So to be able to have a safe travel, what I realized is that we need to have a strong material, and this material could be a carbon nanotube that it provides the highest strength known. And if you're able to leverage that strength completely, then we should be able to build a very safe way to access space. So that was the hypothesis for starting the company. We're taking a step back towards looking at the base, look at why we are trying to create this. The next step was the literature survey to determine, okay, how do we make nanotubes and why choose nanotubes? So with each iteration of studies around it, it started getting more and more ratifications. So it's strong, it's lightweight, it resists radiation. This is one of few materials that can withstand a huge amount of radiation and not get damaged. This is also one of the reasons why carbon containing materials like graphite are used in nuclear reactors for this property. As a bonus, nanotubes offer a lot more properties. They can be semiconductors, which we'll come to in a bit, depending on the size of the tubes, we get their features as a semiconductor. So we can get different band gaps. So we're talking of space, we're talking of electronics, and they also are a water transporter. This is an area where we got significant amount of support from the Karnataka government through Elevate 100 and the central government through IDEX and also through Niti Aayog that has helped develop this particular application further, and which I'll be talking of how it has led to more ramifications. And it exhibits a property called photoluminescence, which has a lot of defense applications. This is a property where the material can produce light in very, very sensitive ways, thermally conductive, and it's electrically conductive. And this property of electrical conductivity is actually being used in batteries. So at NoPo, we've developed coatings that go into space. We've worked on semiconductors where we're actually shipping the material for use in the next generation of transistors. And we also worked on making battery conductive elements. That's a product line that we have. So in terms of challenges we from VentuRISE, all three of them are ticked off from within NoPo's work as of now. And so that way you have more questions that you can ask me. So next step was the experiment itself. So once we had the hypothesis and once we had literature survey that talked about validating the material, next was about going out to build it. Now we will be repeating this process again and again. So in this experiment, the idea was, okay, so we have an idea of how we could build these structures. So now let's go out and build a system that could handle this. So these were the first iterations. We faced a lot of failures, and failures are good because at least if you're failing, you know that you're progressing, you're making something, you're learning what happened. As long as your failures are seeing what is going on, we get to get better and better. This is the same mantra that's also being used. If you look at SpaceX, if you look at how the rocket being built and them blowing up is just considered an RDE, like a rapid an RUD, rapid unexpected disassembly rather than a failure. It's like each of those is actually teaching you more. So before we could produce the first nanotubes, we had to go through this at least 50 times where we kept building reactors, trying to get them to be consistent and stable, but we continued having issues with them, which we had to solve again and again and again. And this solving happened through the scientific method itself. Each failure would be analyzed as, okay, what's the hypothesis? Why did it fail? What happened here? And then do we have a literature survey to tell us what exactly is going on? Do we have something that can help us understand this? And then experiment. And we'd set up the experiments with the help from people. And we have been open to reaching out people from anywhere. So one surprising thing I've found is generally the people who are experts in a field, they're super happy to help anybody. And if you are able to identify who's the expert in the field, who has actually done the work, and you reach out to them, they will be more than happy to help you out. And we were able to find some fantastic human beings like that, that helped us in solving problems and at least providing a guidance on where we could go solving them. So after these 50 and odd, it was exactly the number I remember is about 55 of these failures, we were able to produce the nanotubes. So once we got these, we were super happy. Like this is a zoom of almost a 1 lakh times where we're looking at the nanotubes. Now we were super excited. We have been like very happy that we could produce it, but this was not the end of the journey. We had to go back. We had to again go back and fine tune this. So yeah. So the next step was to again like look at, okay, so now we have a system, we have produced the nanotubes the first time, and now we face an issue. Now we go back again to look at the problem statement again. So for example, we thought we had finished the work, we were getting started with things, and then we realized, okay, we had a failure of a specific component. So this time, for as an example here, we'll talk about the heaters. Now, heaters are a very critical element, and surprisingly, we could find manufacturers who could make the heaters with the specification that we wanted, which meant that we had to go around in circles, trying to identify people, and ultimately we had to end up building them ourselves. Now, during the heaters, we started observing why they were failing. So we realized, okay, we had to solve for this issue. The hypothesis and statement was the heaters are failing and they're melting off. So how do we solve that? Why are they melting? So then we went back to the literature to look for where do we find things on why these things happen and what are some documented techniques that exist on why this is going on. So the standard information sources, Google Scholar is a great source. And reaching out to professors everywhere is another very good source of information. And libraries. Libraries are an excellent source, but today you have digital libraries which you can access from anywhere. So you don't need to walk into a physical library, but you have even more knowledge at your fingertips than ever before. It's really about finding the right information now because there's just so much information out there that you need to find. And then carrying out experiments. These were a lot of burnt fuses as we repeated the experiments to determine how our process modification for the nanotubes is working. And then once we repeated these, we understood, analyzed the data, then went back, repeated it for each component. So we went about doing this on our heaters, we went about designing for pressure systems, we went about it for our data acquisition systems, all of these. And these were all made use of existing off-the-shelf components. First prototypes were built rapidly. So my thesis has been that you should be able to build a quick prototype within 24 hours. And once you have the prototype in hand, then using that knowledge, you should build a more stable system, and that can take a longer duration. So these quick tests helped us determine a lot of parameters. And over time, this was able to get us to produce nanotubes with a very high consistency. So now what these plots talk about are the various uh, data that goes into making nanotubes. It talks about something called the Raman spectrometry, wherein we apply a laser beam onto the nanotubes. And this is one piece of equipment that we got on board immediately as soon as the company was started, because I realized that it's very, very important for you to know what you have done. It's important to know if you're past the test. And if you can determine what is the test to determine whether your product is good or bad, that's very, very critical into iterating through the whole thing. Now, this was the process that we went through, and it's repeated, like it's repeated like so many times. It's just become part of our journey. And so over time, and I'll talk about some of the various parameters so that we had to walk through just to be able to identify how the nanotubes are made. Now, over time, we've been able to develop the nanotubes. We've been able to use these parameters. We've done this is like one of the actual systems. It has undergone a lot of upgrades now from what we are seeing here. And we saw that to achieve these nanotubes in the right form, you have just so many parameters. Like you have over 200 different parameters to optimize, and the process has to be repeated for each thing. So often we think that if you get a product once, it's done. It's not. So you have to look at every single aspect, be able to track every single aspect and compare those data continuously. That's the only way to be on top of this, because otherwise what's happening is like we're creating a material, we're creating a product, and we have no idea whether the product is going to be useful at the end of the day or not. So this is something that we found to be critical, that you have a very strict way of tracking things. We were able to make use of equipment that are present here. Like so, CMTI has been an amazing facility. This is in Pina. ISC again has been excellent with its facilities. JNCSR, they've had amazing equipment, and we've been able to utilize that. So we do not have to build a lot of capital equipment into our cap table, and we were able to utilize facilities that are available around us, which the government has already created. And there's so many centers of excellence that helped us in this whole journey. So the way we went about was for equipment that was not available, that could not be easily procured, we got them on board. For equipment that we could utilize in laboratories, we just went out and bought them. And also, when it comes to funding, one thesis I've seen a lot of people do is to just go out and raise money and think that money is going to solve problems. But I've learned from experience, from looking at a lot of people, that money is not the solution to a problem. Money is just something that will actually most often take you away from solving the problem, because just pouring a lot of money doesn't put the focus on actually solving the problem. It really puts it on how do we spend that money rather than utilizing it. So you need to be frugal, at least in the early stages, until a market has been found. So once you have found somebody who is a customer who can actually take up the product that's been created, that's when we get investors on board, and that's something that will help us grow rapidly. So now using these processes at NoPo, we have created these product lines. So what you see on the left are the nanotubes themselves. Now, this is the same stuff that when zoomed inside looks like those tiny tubes. And these tiny tubes have a diameter of just 1 nanometer. Now, when it comes to this is a product line that we actually provide to customers too. So we sell this to a lot of researchers from across the planet, and this is being used in wide array of works, starting from batteries, electronics, and even for cancer treatments. There are over 135 different applications for the material in the R&D side. The next big market that we have focused upon from NoPo's perspective has been batteries. So nanotubes are used in anodes of batteries, and they're used to improve the performance of an anode. It has been found that when we add single wall carbon nanotubes, it helps stabilize silicon anodes, and that is a major use case. So this is a product line that we have created. And a third product line that we have is something called a single chiral nanotube. Now, these are nanotubes of a very well-defined diameter. So you might ask, why do you want to define a diameter? So as the tube size is varied from the smallest diameters to larger diameters, the band gap of the nanotubes also varies. This is a very, very interesting property. So we have a material where we control the band gap of the material. Now, what this means is that we have a new way of creating electronic devices in ways that were unimaginable before. So you can now create devices with a band gap of your choice. So we can even tune this to the band gap of silicon. So you can have the same control circuitry as silicon and still have a transistor that's 150 times smaller than today's 2 nanometer node. Imagine your phones being 150 times smaller, or your processor having 150 times more transistors while drawing lesser energy than your phone today. That is what this heralds. So suddenly having all these large language models being able to run on a small device in your hands. And the heart of this is the nanotube, and that's being produced right here in Bangalore. So that is what we're able to do. And this uses a process called ATPS. This again is something that we determined from literature surveys because we wanted to develop this technique for use in our water projects. And we came across this technology while looking at literature from NIST, and we've since continued to collaborate with them to develop this further with a lot of insights that have been provided from the open access. And on the battery front too, it was a similar challenge that we looked at. We had to produce high purity nanotubes for use in our water projects, and that led to us creating a material that was suitable for use in batteries. So these were offshoots, and the major advantage has been that we were able to keep our eyes open to look at different other applications for our material, apart from the core applications we were looking at. So far, this has been a conversation on the development of the product itself. Now, when we move towards the scale of how do we get it to the market. So, and one more application that I'd like to showcase here while we talk about it is a sensor that was developed. This was again a prototype that was developed that we have not commercialized, but was created internally again as a rapid prototyping to see if we could create a technology that would allow us to capture body movements and to do it rapidly. So here, what you see is a system where we've connected these sensors to a human hand, and we're tracking the human hand's movements within our Unreal game engine. Yeah. And when it came to creating the systems here, so one of the things that we realized is we always looked for vendors. Like the vendor development was a very critical task because we need such high precision. And getting that precision and getting to find people who can actually manufacture and without cheating you, that's I just put it up directly out there, was a challenge because we had people who would promise to be able to do anything, and then when we actually gave them the project and when we got started working with them, then we realized that they had no idea what they were talking about. But during the sale and purchase time, they had all the optimism. And when it came to actually delivering on it, they had no idea what was happening. So this created a challenge for us. And this is something that we had to walk through. And over time, what we have realized is you need to be able to follow a process. You need to be able to create a set of structured methodologies that will allow you to look at people. So one of the things we found was we could find many of the vendors close by. And once we were able to provide the clarity for them and we were able to work with a couple of them, we were able to identify, okay, this is a person that we can work with. This is a person that actually is reliable. And this is a list of people that I'd be happy to share to like, for each of these components and how we went about it. Welding, we found people that could be helpful for us. And similarly, we found people in other components like electrical systems that could work with us, help us put them together. And this is an ecosystem that we've been building out. Over time, we've also been reaching out to ISRO to see if we could get access to the vendors that have already been approved from ISRO through their stringent processes so that we could use that ultimately. So this has been one area. So while we are here, there are a few questions. So I'll just read out the questions and maybe go through those answers too so that we can move further on this. So there is a question from Shampa Climezy. I think the first one was about highlights on fabrication. So I'm assuming it's fabrication of nanotubes, which we have covered. Since there are multiple use cases, have you thought around doing business in a marketplace as a go-to-market strategy? So that's a good question. So what we have seen as a challenge with nanotubes are with respect to batteries and when it comes to electronics, this has been something that was straightforward. We did not have issues on creating a market. And in several other applications, what we see is customers are ready to take it forward once it's ready in a form where it's all tested, everything's done, and we're ready to utilize it. So that means there is more work that happens from the company's perspective too. So what we have done is to be selective and a little choosy at this stage to choose and to go with customers who already have a requirement in the sense that, okay, I have a use case and I want this material right now and I'm not going to ask you to go out and develop this again from scratch. Because we have seen many of the larger companies too, what they do is they try to offload their work onto the startups, assuming that they're going to anyway do that at their cost, which doesn't make sense. So we look for people who are actually willing to get work done. So that's the way we build out the customers and build out the value at the end of the day, so that as a company that you're able to build things. And there are applications that we have been listing out and putting it out as blog articles. So when someone comes out and says, okay, hey, you know what, this is something that is interesting. This is exactly what we're looking out for. And can you help us out with that? So that's a point at which we start engaging to develop any custom applications. Otherwise, as internal applications, we are focused upon the batteries, electronics, and the water membranes too as a work. So next, we have questions from Rajiv on Rajiv, Deputy Director General. So first one is life is full of trade-offs. Against all the benefits of carbon nanotubes, what are trade-offs one has to live with? Yes, that's a good question. So carbon, like with every carbon material, it is not very friendly with oxygen. So when we heat carbon with oxygen at temperatures of like 500 to 600 degrees, it will burn off into carbon dioxide. This is one major drawback that exists with nanotubes. One solution that people have been working on has been to coat nanotubes with silicon, something called TEOS or silicon oxides. So these generally give protection that allows them to operate at high temperatures. Now, without oxygen being present, they perform up to 4,000 degrees Celsius. So even on high temperature objects, if there is oxygen present and there is no coating support on the nanotubes, it's going to just burn off completely. And a second question was, do the different energy band gap properties of nanotubes play a role in power systems in spacecrafts? Yes, the answer is yes. And they also are involved in generating power too. So there's been a significant amount of work that's happening with nanotubes as solar cells. So traditionally, what has happened is we've used solar cells with different materials that are layered on top of each other with different band gaps. The idea was that each layer of the material would absorb different wavelength of light so that we can capture more light. So the solar cells that are used on spacecraft, the multi-junction cells, they are generally made with at least 3, 4 different junctions of different materials to absorb and create and generate energy with a very high efficiency. With nanotubes, that's potentially something that's done with a single layer. So especially the single chiral nanotubes with specific band gaps that allows us to layer them up. And they do play a role like, so when it comes to systems like wiring within the power system, that's an area where nanotubes are utilized that are being evaluated significantly right now. And especially this evaluation is happening in the US, where they're being seen as an alternate for copper in conductive lines. So this is still an ongoing work. There's still a lot of problems to solve, and that's going on here. So next, there's a question about the impact of cryogenic temperatures of less than 4 Kelvin on the nanotubes from Murli Kandlagunta. So, Murli, so what we have seen is even at the lower temperatures, nanotubes themselves are quite stable. Nothing happens to them. But when they're used with epoxies, the epoxies start cracking. So that's an issue that exists. Nanotubes at these lower temperatures, in fact, have been used to confine atoms inside them and to study their properties. So one of the interesting aspects is once you have an atom inside the tubular structure, so that is more stable. And you can actually, there's one company that's even working on entangling atoms inside a nanotube. So there's a slower decoherence and you can use it for quantum computing. So there's a lot of cool stuff being done. And at very low temperatures too, these materials work very well. They have no issues. Next, there's a question from Vaibhav Bhatnagar. Vaibhav from Ardhan Research. We are in hypersonic space and are looking for a carbon-based material that brings inherent radar and EM absorbent capabilities. How does nanotube fare on these parameters? Additionally, can CNT be mixed or combined with titanium aluminum alloys? Yes, answer is yes. And I can share like a few data sets that I have been able to gather. Now, the nanotubes that we make at NoPo, we also use iron as a catalyst. So because of that, inherently they have iron. And as you might already know, microparticles of iron are used in radar absorption coatings. So almost every Russian radar absorption coating materials, they make use of these tiny particles of iron. And this is something that's a byproduct for us. Like it's not really something that we did as like something we wanted to do, but we developed a process for doing that because we need to produce nanotubes for this. And this exists. So yes, it is possible to electromagnetic absorption capabilities with nanotubes. Another interesting thing that I've learned about, but this has been like knowledge gained from secondary sources, so I can't really attest to it, is that these are materials that are actually used on radar absorption coatings on stealth aircraft, the F-22s and stuff. So we've heard that they've used single wall nanotubes for some of the secure areas. And since these are already classified, there isn't much literature about it. But as a microwave absorption material, it does very well. And it's also very good at infrared absorption. So that's also there. And in creating alloys, the answer is yes. It just comes down to what exactly you're looking for, in the sense that the question is, can it be mixed to combine with titanium aluminum alloys? The answer is yes. And it again comes down to the specific application, specific use case, and how we are looking at it. And when it comes to nickel alloys, they're even better when it comes to working with nanotubes. Nickel and carbon seem to have a very good bonding. So that's that. So those are the tech side of things. So next we'll move on towards the customer side of things. That's all the questions we have right now. So the next question was, okay, so that I was looking at answering was, say, so we have a way of creating the material. So we have made the material. Now we have its properties tested out. We have repeatability demonstrated. We have product lines demonstrated. Now who's going to buy this? Now with deep tech, that's one other scenario. And this is a deep tech problem that exists from the start, even for penicillin. Penicillin was discovered. We all know that Alexander Fleming won the Nobel Prize for it. It has helped save numerous lives. Even today, a lot of people are saved because of it. But penicillin did not become an overnight success. It required over 15 years of development with significant amount of money being poured into it to identify ways to actually scale it up. And its use case became very, very predominant when people realized that they needed to have this during the battlefields. So the World War was the trigger to actually get penicillin outside. And similarly, it was the army that became a trigger to get IC-based devices outside. So one time I was in the valley asking around people to identify, okay, so how did you sell the first transistor? And how much was the first transistor sold for? So this was like something that was interesting. Like, okay, how do you get nanotubes and how do you put them out there and how do you get it to a first customer? Do you then grow from there? Now, this was an interesting challenge. Now, you'd be surprised to know that the first transistor, like we're talking of just one transistor. Now, phones that we buy today, they have 100 crore transistors inside them. And we're talking of selling the first one to somebody before we sell 100 crore to anybody. And this somebody became military and they were willing to pay $20,000 per transistor. And the reason they were willing to pay such a high amount was because they could use it on their missiles. Otherwise, they had to use vacuum amplifiers. Vacuum amplifiers took up more weight. The moment you switched to transistors, you could save on weight. Every additional weight could now become the ammunition. So that is how they were able to justify spending on it. And that's how they were able to grow that. Now, one interesting aspect is like when we look at it, like, okay, so something was $20,000 in the 60s, and today we buy 100 billion of them for far less than that. So, how did that happen? So, how did something that even today we can buy a phone for 20,000 rupees and we still have so many more transistors? Whereas then you're paying like so much money just for one transistor. In today's money, talking of paying so close to 20 lakhs for one transistor. So the justification for that actually comes from one secret sauce. And this is something that's also out there for us to see. And this is something I came across while spending time at the Singularity University. Now, this secret sauce is basically this trend that seems to be applicable across sectors. So we've all seen Moore's law, and we have seen how Moore's law for computers talks about how computing capacity has been doubling every 18 months. But post the mobile era, 18 months has been squashed, and now we are doubling everything every 9 months. And with flagship phones arriving every year now and even sooner, so things are doubling even faster. Now, what is interesting is that this trend where something doubles in its capabilities while the price remains the same, this is known as a exponential technology. There are several technologies, and it seems like almost every technology follows this trend. With solar cells, batteries, electric transistors are something that is more visible to us, solar cells, biotechnology, space, all of them seem to follow this trend when we start plotting logarithmic plot. And it also seems that even life seems to do that, that we seem to be doubling in our technology capabilities every couple of years. And this has been accelerating, or we are able to see those results even faster now. And this is why we are able to see so many revolutions so quickly. So imagine that we've just learned to walk about a crore years ago. And now we're already working with a device that's doing all the jobs for us. And this is how much time it has taken us. And but from the time we have invented the steam engines to today, we have been able to double things so fast. Now, what the value has and what we do not see is this projection of looking at the future and being able to calculate when this doubling is happening. Imagine building a business where you know that in the future, this is the price point things are going to reach, and you're building in enough flexibility into your designs that you incorporate these changes. The same thing was the reason for going for electric cars, because electric cars, to people observe these trends that every 3 to 4 years, battery prices were halving. So you're getting double the capacity, same size battery pack, same price every 4 years. Solar cells are doing the exact same thing. Now, this doubling effect is something that we actually are tuned to, like our brains are actually designed to handle these logarithmic plots. But over time, what has happened is we have gotten used to something being more linear. We're more comfortable looking at something which says, okay, I'm going to improve this many percentage. But then this compounding is something that has become something that's a second nature, that's much more harder to reveal and see through. So if based on any field that you're working on, any technology that you're working upon, if you're able to track this and if you're able to look at, okay, what is this trend, and you're able to anticipate the future requirements, there's nothing like it. And that's how you can build customers for any kind of deep technology. And even with the nanotubes, when we started with things, we did not have very clear visibility. We just knew that there are other fields. The other fields are also moving rapidly, and there are requirements created across them that is helping them move further. And this is something that helped us anticipate certain applications in the future by having early works being done. We could not anticipate every application. We, for sure, we were not able to anticipate that it's going to be batteries or electronics. But over time, we were able to get these things in place. And today we have seen these use cases where we started with membranes. We have found a use case in space, which is for black coatings on them, but the market size is small. So when you have to start balancing out the revenue aspects with the technology, you have to start making hard choices. We develop things, and we can also be improving upon them. And similarly, electronics, energy storage, drones. Genetics is another very interesting area where people are even looking at structures that allow for human-machine interfaces. That's another exciting area that's happening. So nanotubes are biocompatible, which means that you can actually directly utilize them into connecting to biological structures. So these have been some of the application areas that have come up as we work towards improving the nanotubes and getting them into more people's hands. So the customer search really starts from identifying the exponential and creating the solution that meets these exponential requirements and being able to have the patience. So these are all patience games. It's a decade to 2 decades of work wherein you build a massive amount of expertise and able to deliver that. And if things happen faster, that's even better. And it also helps a lot to have a larger company working along with you because a larger company can set the requirements, and that's actually a sure shot formula to grow into a revenue generating unicorn very quickly. So this is how you find the customers. This is how you develop the technology, starting from scratch, put it together by building out the ecosystem around you, reaching out to everybody possible, and sticking to the scientific method of solving problems. For finding customers, especially future customers, you can anticipate them by looking at the exponential they're following and looking at how you can leverage those exponentials to your advantage. And all of this comes down to being a patience game. So this is all from my presentation for today. And from the masterclass, and I'd be happy to answer more questions and to go through that. And I'll just go through the next set of questions that are there meanwhile, and feel free to type in your questions too. Okay, so we have a question from Rajiv Gambhir on your information about single layer space grade solar cells and panels. Is there a commercial solution that is available with this technology today? And how does this fare commercially against the current commercial solutions? Yeah, so that's a good question, Rajiv. So the commercial solutions, these have been under development for over 50 years. So there is definitely a huge lead time. And as I was talking about these exponentials, the nanotubes are catching up. They are doubling in their capabilities. Right now, commercial solutions are nowhere near the existing solutions. They're quickly catching up. There are specific users who are looking at using the nanotube-based solutions because they're just lower cost to start with. Efficiencies are improving as with through each iteration. That's all that's happening. Yeah, so we have a question from Sundar Rajan. So the question is, will you speak a few words justifying the title of today's talk? What does it take to build a 100% of deep tech company from India? So what are challenges to build the startup and scale it up? Sure. So Nagarajan. So we started out like the whole journey from within India. So as I said, I'm from Bangalore, and as we started building out the nanotubes, the first thing was getting started, finding a space to be able to start building things, and figuring out what regulations are there, and if regulations actually prohibit you from building anything. So this was one I thought was a deep roadblock that existed because many people that I spoke to said, okay, I'm not going to build anything because I don't know if it's illegal to build or not. Now, the thing is, when it comes to research, you're actually creating something where you do not yet have regulations kick in that. So that's something that you can carry out. Now, the next thing was when we started building out these systems itself, when we started building out these reactors, started building out the controllers, and we started building out the alloy systems that go inside them. So these were all actually developed here in Bangalore. So one time, for example, we got a specific alloy rod, which had to be machined into a reactor, and we had to perform an operation called a gun drilling. This was basically to drill a 2.5 meter hole inside a solid rod of a very strong material and be able to create a reactor from that. So we ended up looking at a lot of options, and finally we found one vendor in Pina. We sat with them, and he was scared of putting this into his machine. And we were like, okay, you know what? Let's do it. Let's give it a try. Let's see how far we can do. Took us over a week, but we were able to finally accomplish that. We were able to build that out. So on the material systems, we were able to do that. We carried out the work. All of the control systems, electronics, these were built here. These were again built using off-the-shelf components. We used them as controllers and systems. Then we built them to control our nanotube producing reactors. And the algorithms, the software, all of it was built out here. The materials that were used for it were all procured locally and built out from here. So when it comes to developing the technology in terms of how do you build a system that's capable of withstanding such a high temperature, pressure conditions, that knowledge base was created out of here. The procedure that we used for it is the general scientific method. We didn't have to invent a new methodology for creating it. The building of it was what was done here. Yeah. So there's a question from Vaibhav from Resus Inosol. I wanted to ask about the IP seed maturity in India and how serious it's taken in the Indian market, especially with the lack of IP management, companies, and weak enforcement mechanism. If one doesn't want to go into operations, is there a market for IP? This is a good question, Vaibhav. So I have a bit of maybe a controversial answer for this. The IP scene in India has actually matured a lot. The answer to that, yes, it has. And taking it seriously, so that I don't see much. Because what happens is when you think of any of these harder technologies, the number of components that actually go into achieving the end result is just massive. Now, for a larger company that's looking at patents as a portfolio that's going to help it out, like say if you have a design patent that you're looking at, you want people to infringe on your design, it makes sense. But if you have a process and you're looking at not infringing the process, it's hard to even reveal all the parameters because putting out a patent out there is actually revealing more data. And if you look at the landscape for carbon fibers, you will see that carbon fiber patents started vaporizing rapidly. Like right after the 90s, you don't see much patenting literature with the carbon fiber. Now, that does not mean that carbon fiber field has stagnated and there's no IP being generated. Now, the few companies that own the technology, they've decided to keep it internally because that seems to be an even better strategy than to even release it. It's just like that the number of steps involved, the number of parameters that go in are just so hard that it doesn't even make sense to patent them. But in a sense of showing that you have the IP, it does make sense to put out patents, especially if there's an application that you think anybody else could replicate. And also, right now, the trend is to have patents as a way to protect yourself from somebody else coming and suing you for it. Other than that, it doesn't do. And if you remember, there was one interesting aspect where Tesla said that they put out all their patents and said, okay, all our patents are yours. And then they put a fine print in there saying, okay, if you're going to use any of our patents for any of your work, you can't sue us. So that gave legal protection to them, so that they they said they didn't want to like patent, but they still wanted protection. So that's just what happened. This is one way that people have been looking at this. So I hope that answers your question. And
looks like we don't have any more questions. Vinay?
Yes, so it's a fantastic session. There was a lot of learnings and takeaways. Thank you, Gadadar, and thank you a lot of your startups for taking the time, and also NoPo for pioneering the whole the advanced high precision carbon nanotube production from India. There are a lot of takeaways. So what we'll do is we'll also share the webinar on our YouTube channel. I hope it's fine, right, Gadadar?
yeah,
Uh,
that should be
I,
fine.
that should be
I'm
fine.
just wishing that my engineering classes were as interesting as this one.
Yeah.
Right,
In fact, Q&A,
it took me back to my engineering classes at NIT Surathkal. But yeah, this was fascinating stuff, Gadadar. Thank you so much.
Also, I think,
This is Anand here.
yes, sir.
I just wanted to, on behalf of my Bangalore and the Matrix Forum also, I wanted to thank you, Gadhadar, for an excellent and a very lucid presentation on not just the opportunity, but also the process that we follow, which is very scientific, and also make from India for the world, which is what I think is the basis of VentuRISE is. And we really want to identify opportunities and companies and promote them from Karnataka, from Bangalore. That's the VentuRISE vision. And also to bring in the ecosystem. You clearly mentioned that there is enough of the ecosystem that's available. I also wanted to add that the entire defense aerospace sector have all been opened up. And I think clearly quantum materials, life sciences, AI, all these are interdisciplinary in a sense, and they're also interdependent. And there are plenty of opportunities for startups. Very exciting. Thank you once again for volunteering your time. Over to you, Vinay.
Vinay, you're on mute.
Sorry, yeah. So I've just shared the link of the areas where VentuRISE is focusing on. So it is ESDM, it is electric vehicles and clean mobility, as well as aerospace and defense. There is a lot of details on the link. So for those of you who haven't applied yet, please do apply. We have a very limited short time, and the process of reviewing the applications has already begun. And for those of you who haven't completed completely, do go to the F6S website and see areas where you could complete. We have a team that is very actively answering your question answers. For those of you who already know about VentuRISE, just click on this link and apply for your startup. Robotics could be, because I think you may find use cases in EV and clean mobility. There are quite a few robotics use cases in that space, so you might want to look at it. And many founders are also tweaking what they've already built to solve some of the use cases. Could also be in defense, aerospace. As Gadhadar mentioned, some of the first set of products are built. He spoke about Alexander Fleming of penicillin. So the first set of products are built when you're able to come up with use cases in some of these, more exciting spaces where innovation is happening. So you might want to tweak your offerings.
I think there was a question somewhere around, alignment to the problem challenge statement, which I kind of addressed on chat, but I just want to pick that up, just add to what Vinay said. So the way we went about this, we actually collaborated with industry to say, hey, look, what are the 3 or 4 big kind of challenges that need to get, solved? It is on that basis that these challenge statements are put together. We recognize that there will be some startups who may already have a solution in that space. There may be others who may know how to solve it, but they're currently probably in an adjacent area. But there is a way in which, some and to go back to Gadhadar's point about using the scientific method, there may be ways to actually tweak that to, repurpose, for want of a better word, the current solution to solving a new problem. So we are happy to look at those kind of situations as well. Yeah.
Right. So does anyone have more questions, queries you want to clarify around VentuRISE? There is a process. So those of you who apply for it will go through, we have the Thai Global Summit, which is happening very soon. And we're going to have a lot of mentors and domain experts who are going to be there. So we will have a day-long session for VentuRISE startups, especially on these tracks. So I just shared the link of the Global Summit for you to take a look at it. And we will have some engagement activities at the Global Summit as well.
So I think we had scheduled, did this till what, 8:45, Vinay, was it?
Yes,
Or
we
is
have.
it 9 o'clock?
And being a Saturday, we'll also, stick to time.
Yeah, so
Yeah.
yeah. Super. So I think if you have kind of answered all the questions, hopefully, is there anything? Yeah, looks like we have answered all the questions. So there is enough and more happening about VentuRISE. You will find information on the VentuRISE handle on LinkedIn. You can also kind of reach out to us via the F6S page, or you can write to us at venturise@tibangalore.org. We'll be happy to answer any questions that you may have about the challenge and the upcoming Thai Global Summit as well. Yeah.
Yeah. So here are some links. You can just take a look at it, and you can email us at venturise@tibangalore.org in case of any queries. So with that, we would like to thank you all for your time. We would like to thank Gadhadar for the masterclass. A lot of takeaways, just trying to put it together, and we will repurpose and reshare it with the community. Thank you so much. Thank you, everyone. Have a great week.
Yeah. Thanks, Vinay, for putting all this together, right?
Yeah.
Great job. Thank you.
Thanks.
Bye-bye.
Yeah,
Good night.
thank you all.
Yeah, bye. Thanks, Gadhadar.